When you picture a chemistry lab, you might imagine scientists working to isolate perfectly pure elements. But in the real world, absolute purity is incredibly rare. Almost every substance we interact with is a mixture. Take copper. Mix it with zinc, and you yield brass. Add nickel to the vat, and you create German silver. Swap those out for tin, and you forge bronze, a material so resilient it defined an entire era of human history. The specific ratio of the components dictates exactly what the material can endure. Out in the foundries, metallurgists rely on these exact measurements. They manipulate the percentages of different metals in a molten vat to control the exact melting point, strength, and flexibility of the final alloy. The stakes remain high, even down at the microscopic level. If you dissolve exactly 1 part per million of fluoride ions into your drinking water, it actively prevents tooth decay. But if you push that concentration higher, those exact same ions become highly toxic. Sodium fluoride, in heavy concentrations, is a common ingredient in rat poison. The strict ratios defining these homogeneous mixtures act as the precise dividing line between a useful tool and a lethal hazard. This mathematical tightrope is constantly being walked inside your own body. Human biology operates entirely on liquid solutions, and getting the concentrations right is an absolute matter of survival. Think about an intravenous injection. That saline bag contains water carefully calibrated with specific salts to hit exact ionic concentrations that must perfectly match your blood plasma. If that IV fluid is mixed too strong, it pulls water out of your cells, causing them to shrivel and fail. If it's mixed too weak, water floods in and the cells burst. To prevent these system failures, we have to understand the specific rules governing what chemists call binary solutions, mixtures of exactly 2 components. Our lives quite literally depend on the invisible mathematics balancing the things being dissolved, the solutes, and the liquids doing the dissolving, the solvents. By definition, a solution is a homogeneous mixture where the composition and properties are uniform throughout. The component present in the largest quantity is the solvent. Whatever you drop into it to dissolve is the solute. But you cannot simply mix any 2 things together. There's a strict rule of solubility. Like dissolves like. Polar solutes, like salt, readily dissolve in polar solvents like water. Try mixing salt into a nonpolar solvent like benzene, and it simply sits there. The intermolecular forces must match. Even when those forces do match, a solvent can only hold so much. When a liquid has accepted the absolute maximum amount of solute possible at a given temperature and pressure, it reaches a state of dynamic equilibrium. In chemistry, we call this a saturated solution. In daily life, we might casually call a mixture concentrated or dilute. Subjective descriptions are useless if you're engineering a bridge or dosing medication. We need strict quantitative metrics. This animated diagram breaks down one of the most common metrics for liquid mixtures, volume percentage. You divide the volume of your specific component by the total volume of the whole solution, then multiply by 100 to get your percentage. For complex chemistry, we use mole fraction. This animated graphic visualizes calculating the moles of one component relative to the total moles in the mixture. No matter how many components you add, the sum of all their individual mole fractions always equals exactly 1. By translating physical ingredients into these universal mathematical units, we can calculate exactly how a mixture will behave long before we ever combine the chemicals in a lab. One of the most critical behaviors we can predict is vapor pressure. At any given temperature, molecules at the surface of a liquid will vaporize, exerting a specific pressure over the liquid phase as they reach equilibrium. In a pure liquid, the entire surface area is occupied exclusively by solvent molecules, escaping freely into the air. Add a solid solute, and new particles physically block solvent molecules from escaping. Evaporation drops, and the vapor pressure goes down. The French chemist François-Marie Raoult codified this behavior. Raoult's law states that the vapor pressure of a solvent in a solution is directly proportional to its mole fraction. As you decrease the mole fraction of the pure solvent by mixing in more solute, the vapor pressure drops by a mathematically exact, predictable amount. Chemists classify this lowering of vapor pressure as a colligative property. That means the physical identity of the solute is irrelevant. The pressure drop relies entirely on the sheer number of particles you've added to the mix. By simply dissolving a solid powder into a liquid, we physically rewrite how that liquid interacts with the atmosphere around it. We exploit these specific properties every time we drive a car in the winter. We pour a precisely mixed 35% volume-by-volume solution of ethylene glycol into the radiator to act as antifreeze. This thermometer graphic tracks the colligative effect in action. By mixing in that specific concentration of ethylene glycol, we force the freezing point of the water in the engine to plunge from 0 degrees Celsius all the way down to negative 17.6 degrees. If that specific ratio is miscalculated and the mixture is too dilute, the water freezes anyway. It expands, and the immense internal pressure cracks the solid metal of the engine block wide open. Whether we are using solids to lower vapor pressure or dissolving gases into liquids under pressure, according to Henry's law, the core principle remains the same. From the precise ionic balance inside a hospital IV bag to the coolant circulating under the hood of a car, these chemical rules form the operating code of the material world. Ultimately, mastering units like molarity or mole fraction gives us the power to control the exact chemical ratios that keep our machines running, our environment stable, and our bodies functioning.